this technology can collect the real-time data. This real-time data really give you the clue about what happened between today and then the day in next year, because they really capture everything that happened. And then you can, using this data, really improve our understanding about this physical cause of this change.
Welcome to Growing Impact, a podcast by the Institute of Energy and the Environment at Penn State. Each month, Growing Impact explores the projects of Penn State researchers who are solving some of the world's most challenging energy and environmental issues. Each project has been funded by the Institute's Seed Grant program that grows new research ideas into impactful energy and environmental solutions. I'm your host, Kevin Slyman. The Earth can shift and move in a moment. Sinkholes and landslides can occur without warning, causing damage to property and injury or death to those in the area. But what if there was a way to recognize the danger before it struck? In this episode of Growing Impact, we look back on a seed grant project from 2019 that uses fiber optic cable to identify potential geohazards. As the project continues to grow, it's finding new opportunities to collect and analyze data in amazing ways, like on flooding and even the movement of people. And it's all thanks to an innovative idea to use fiber optic cables that are already buried in the ground below us.
Hey, Kevin, how are you?
Good, how are you?
Yeah, I'm doing good.
Thanks so much for talking through this. We really wanted to visit some of these older seed grants. And I mean, your project is just a great example of something that got legs and has really moved forward. And I'm just interested in learning more about it. So thanks so much for taking time to do this. Can we start with you introducing yourself?
Thank you, Kevin. I'll be very glad to be with you today. So I'm Taiyuan Zhu from Geoscience Department. I'm associate professor. I'm interested, how our Earth's near surface be modified by external impact. For example, the short-term climate change. How does that impact our Earth's near surface? I basically using the geophysics tool, theory and a method to understand the physical cause of this change. With that, we can understand what caused the geohazards, for example, sinkholes collapse, and what caused the water, go from the surface to the deep earth. What that happened? What's the physical, process of that? So that's my primary interest.
The seed grant project that you applied for years ago really took off. It focused on using fiber optic cables, like the ones used to provide internet access, for seismic monitoring and to improve hazard assessment. Can you talk us through that? Talk about the, how you even thought that could fiber optic cables be used in this way? And then just kind of talk us through a little bit of the science and help us understand it.
The fiber optic cable sensing using the fiber optic cable is a very new, research front in geophysics. Back to, I think, 10 years ago, oil and gas industry start to look at this new technology, see if that works for oil and gas wells, because it's very difficult to put the conventional sensor in the wells, because the well is so limited space. So this technology basically can detect the very small change in anywhere when the cable can access. It's very easy actually put the cable down to the borehole versus conventional sensors, because sensors is always have certain volume, but the cable is just as thin as your hair. So it's easy attached with a casing and then lower to the very deep borehole. So that's the original, idea kind of born in geophysics community. And then back to 5 years ago, when I initialized my research, I'm just asking, can we using, existing cable, for example, that already been deployed in city for telecommunication purpose? Can we use that for geophysics research? Instead of go to the borehole, can we just do in the pipeline, in the, conventional city, infrastructure? The big reason is in our urban city, it's very difficult to put a conventional sensor in subsurface. There are lots of issues with permit. There are lots of issues with security, and also it's too costly to put a conventional sensor everywhere. across one street block. But the cable is everywhere already deployed in the pipeline. Telecommunication industry already spent, $1 billion put everywhere in our city. So that's kind of the idea. If we can combine, existing infrastructure for, geophysics sensing research, that be gonna, at that time, I just see this gonna be a great deal for us and also a great deal for research in urban cities.
Can you talk a little bit about the science behind it? So you have all this existing cable throughout cities and under streets. How then do you utilize that, and what other things do you need to do to actually gather that information? Can you talk a little bit about that?
The telecom fiber optic cable is basically made of the glass. But if you look at using microscope, there are lots of little, we call the scatter or impurity in the glass, in the nanometer scale. Okay. So when you send the laser through the cable, the telecom message basically pass through from State College to New York. But there, only 5% or 10% energy actually backscatter back to your sending place. For geophysics, if we send something to location A, we really want to know, how far that location to us. If we know that information, so if something happened at the location A, we can know where that happened. So the basic principle gonna be, you send a laser to the glass, through the glass, and then energy gonna kick back. And then we're gonna analyze this laser energy to understand, where that something happened, at which location, and how much of that magnitude is based on the laser power.
Interesting.
Yeah.
So if nothing is happening, you get kind of a baseline reading. But if something happens, you then start getting more kickback or feedback, I guess, of some sort. Of
Exactly.
that. Okay, got it.
Exactly. For example, I can give you a simple example. For example, is there earthquake happen?
Mhm.
The earthquake gonna shake the ground. When you shake the ground, that gonna modify the fiber optic length. For example, we call the strain. If that strain be modified, we can detect, how much, the length be modified. So we know where that be modified, and then how much of the strain over there. So that tell us, when the earthquake hit this area, how much damage you can receive. So that's a very key information, because we always want to understand, when the earthquake something happen, how much damage you can expect at a particular location.
Wow, that's amazing that you can calculate that much from the feedback that you're getting. Well, that kind of brings us to the next question of, so you mentioned earthquakes. What other sorts of seismic hazards or happenings or geological events maybe can be detected?
Because we know the geophysics principle of this technology is so cool, can detect some damage at a particular location. But what else, signal we can record? So that's actually our first question in our proposal. And then, we started data recording back to, 2019. And we actually saw lots of amazing things. For example, the first signal we saw is from the thunderstorm. The underground cable even can listen the thunderstorm. The lightning thunder cross the State College. We see a beautiful, the movement across the State College. That's never be achieved in meteorology community, is because their radar sensors or their, meteorology sensors is 2 kilometers away, for example. Across the whole State College, they only have 1 or 2. So, for example, that's a kind of like a severe weather information.
Mm-hmm.
The second new signal we discovered from our data is the flooding information. When the severe weather pull lots of water in the ground, people always want to know, where the flooding prone areas, right? And we look at the cable, the water gonna pull into the sewer. So that actually generates a strong energy in our cable. We saw that energy.
Wow.
And then what we do is we analyze, how big is that rain? From the weather station, we know how big is that rain, and then we compare our data energy, and then we do we call the cross correlation, and then we analyze, in this particular rain precipitation corresponding to this kind of energy. And then we can understand, using our data to understand, how much water you're gonna put on the ground. The recent one, my student just working on the manuscript is we look at the potential sinkholes because we found that using the cable, in total is about 4.2 kilometer long. So with that information, we actually can image the whole subsurface along the cable, and then we analyze our results to see some potential we call the low velocity zone. So that's a low seismic velocity because you do have a cavity compared to you have limestone rock. So rocks propagate seismic velocity faster compared to air if that's a cavity. So we actually can detect that a low velocity zone. So that tell us, here is a potential cavity. And then if you go to the surface, you look at the soil thickness, you can tell, this is a potential, sinkhole development area. At the beginning, we don't know all these hazards we can detect. But, when we look into the data, we found that there are lots of potential to help us to, really detect these geohazards.
Does your technology offer early detection that can provide a community with time to respond before an event occurs?
I totally think so. I just give you one example about the sinkholes, potential sinkholes. This is because, as I said, the technology can help us to image the subsurface velocity structure. If we can identify the more cavity under particular location, this cavity information in the certain depths is really a key to protecting this collapse. So that's kind of my understanding how this knowledge we study, we invested using our data can help the geohazard prevention.
Could you talk a little bit about what the inspiration was to using fiber optics in this manner?
So when geophysicists start to use fiber optic cable, they always use a new fiber optic cable. So that means we purchase the new cable from the telecom manufacturer, and then we deploy in somewhere for geophysics monitoring. But our research is really take advantage of we call the dark fiber. So the fibers are unused for telecommunication, but is already deployed in our cities.
You're taking advantage of what you're calling dark cable. So these are ones that are not being used for telecom purposes currently, but they're deployed, but they're not being used.
The 10% of the fiber optic cable is unused. This cable is used for backup. If there's anything emergency happens, they're gonna switch the cable. That don't gonna disturb our phone call, our internet, is because they do have some backup cables over there. Because that, luckily, because that's 10%, that's why we do have lots of dark fiber in underground, pipelines. If that, only let's say 1% or 0.5% can be used for geophysics research, that already, a big deal for geohazards monitoring in city.
Where are some places where this monitoring system has been utilized, and can you share some success stories around it?
So far, we did experiment in State College since 2019. We also got supported from NSF CV program to demonstrate technology in Pittsburgh, Pennsylvania. So we also want to replicate, the research in the larger scale city. Can we really observe something similar signals in Pittsburgh? Can we really see the flooding signals over there? Can we see the landslide signals? Can we also detect the cavities, sinkholes in Pittsburgh? So that's kind of the research question we are trying to answer in larger scale, experiment.
Could you talk a little bit? Who are some of the groups that could benefit from this technology?
I can imagine many of city planner or management groups can benefit the technology in terms of city geohazard prevention. For example, the water authority, they can use our information to determine the flooding zones in city. For geophysics community, I think our study also can benefit other people's research because we publish our research discoveries about these geohazards. I believe in next few years or decades, if the similar, if other cities, for example, have the similar geohazard issues, they may can look at, because again, the fiber optic cable is everywhere in our cities. This is not that difficult to replicate in other place.
So this research, do you consider this an open source, kind of like a giving back to the community so that, others can benefit from this technology? Once that's created, is that something that you're looking like, yeah, now other communities take advantage of this to benefit your communities?
For sure. I think, two ways. One is benefits to our community by sharing the data, sharing the research results, and, talk to colleagues and let them know the lessons we learned, from this project. And also can benefit other communities. For example, when we look at the flooding, signals, we actually want to gather information from engineering, because they really design the sewer system. We want to gather, information about how big the Earth's sewer hole, how deep. This information help us to calculate how much water getting into them. So that information actually also help us to calibrate our signals. I
Mhm.
think this is kind of like a mutual benefits to different communities, because I believe our data is also useful for engineering people to really design some appropriate, sewer in the future if they build a new city. But at the same time, we using their information as a kind of like a ground truth or some information, really calibrate our data, because our data is again matter stream, is a geophysics or physics unit, is not a water unit. If you want to use that for the water, you really want to do the, very accurate calibration, and then can serve that community using geophysics data to solve the water issue. One exciting discovery is using we call the noise data to understand the human mobility during the COVID-19. So when we look at the data during the COVID 2020, we actually found the data we call the noise level is very low compared to few months ago in 2019. But when we really look into, when that noise level really changed, we found in State College is about, March 15, 2020. That's exactly the spring break we are here in 2020. And then we look that and see, even after spring break, the noise level still stay very, very low. And then we realize, it's because of COVID. So the university actually shut down after the spring break. Students all won't come back to the university park campus, and then that's kind of help us to say, our data is really can also help to understand the human mobility in the city area.
Could you talk a little bit about how the early support from IEE enabled success in this project?
I really appreciate, IEE City Ground can help junior faculty initialize some new ideas. Back to 2019, when I received the IE City Ground, it really can help me purchase the equipment. And then once we got equipment, we can have data collection. Without this new, equipment, we just cannot get any data collection. IE really provided that, resources to me. Even now, we actually use that equipment for Pittsburgh project.
How has this project evolved since getting the IEE seed grant?
Luckily, we got a big project from NSF Signal in the Soil. That's a $1.2 million project. So that actually helped us to set up a new project in Alaska to understand actually permafrost degradation. So we deploy the fiber optic cable in the Barrow, Alaska. It's about a 2 kilometer long, and we collect the data. Even until now, we already collect the 3 years data. So we saw lots of interesting signals about the permafrost degradation, in particular about the ice wedge cracking, and also the iceberg break. on the ocean floor. So that's kind of amazing, research direction, I'm working on now. But if we think about how this, project evolved, is really with, big support from the IEE. And then we do get the equipment. And then using the equipment, we can do more data collection and also more interesting or some other interesting, research directions we can test or we can demonstrate is that this technology really can work for, permafrost degradation study. We never
Right.
thought about before, but once we got a experience in state college, we build up confidence. We see, oh, it is really possible. Can record some, very small signals because the technology is really on the laser in the nanometers. You have a very small, environmental change because the sensitivity of the laser that it can still detect this small change. For example, permafrost degradation. You just cannot see it. For long term, you can see it, but for the short term, you didn't see the degradation. Where is the degradation? But because our, equipment, we actually can see it from our data results.
That is fast. I mean, that is amazing. This technology has so many connections and abilities to learn about our world, from moving people to moving water to moving land.
Yeah, this is exactly, why, I'm really interested, how the Earth's surface or Earth's critical zone being modified by something. Because in the short term, this modification is really hard to capture by our traditional sensor. You can imagine you collect the data at today, and then you don't collect data tomorrow or day after, but you collect the next year. And then when you compare this data, you actually don't understand what physical happened between today with that time, because there are lots of things going on. But if you have this technology can collect the real-time data. This real-time data really give you the clue about what happened between today and then the day in next year, because they really capture everything they happen. And then you can, using this data, really improve our understanding about this physical cause of this change. So that's the amazing of this technology.
Thank you so much for being on here. I really enjoyed talking with you. Thanks so much.
Thank you, Kevin. Yeah. If you want to reach out to me, please, email me by tyzhu@psu.edu.
This has been Season 5, Episode 5 of Growing Impact. Thanks again to Taiyun Zhu for speaking with me about his project. To watch a video version of this episode and to learn more about the research team, visit iee.psu.edu/podcast. Once you're there, you'll find previous episodes, transcripts, related graphics, and so much more. Our creative director is Chris Komlenik, with graphic design and video production by Brenna Buck, marketing and social media by Torian DeViro, and web support by John Stabinger. Join us again next month as we continue our exploration with Penn State research and its growing impact. Thanks for listening.